Okay, so hello everyone. Welcome to the yet another weekly robotics meetup. Today with Denis and Bence talking about ROS2 control. The format will be the same as usual. So we'll first have the presentation, and then we'll have a round of questions, about 15 to 20 minutes usually. But we'll see how the discussions evolve and about the timing. Yeah, so to you, Denis and Bence, the floor is yours, and let's get it started. I'm really looking forward to learning from you today.
All right, thanks very much. So I'm going to be doing most of the basically introductory slides, and the hard stuff I'm going to leave to Denis. So yeah, let's get started. So today we're going to be talking about ROS2 control. If you have a little bit of history with ROS, you may have heard about ROS control, which is an earlier iteration of this. So we're actually going to start with that to have some concepts to build on. So Denis did not allow me to crack the same joke that I played on one of the previous presentations with it. In that one, the outline, the first point of the outline was telling you how the outline looks like. But so yeah, in general, we're going to go through about like the motivation, some history, some of the basic concepts of ROS control, some of the usages, and some of the drawbacks, basically telling you the story of like why we really wanted to go through the whole hassle of reinventing our own wheel. And then we're going to go into some more details about ROS2 control itself. And hopefully we're going to have some promising examples as well. So buckle up and let's go to the next slide. All right, very brief introduction of the two of us. So about myself, I've been involved with ROS control and ROS2 control for the last 5, 6, 7 years, something like this. It all goes back to the time when I was working at Robotics, and like the origins of ROS control, one of the origins of ROS control, or origin eras of ROS control was there. Currently, I'm working at 5AI as a lead software engineer. We do self-driving car technology. So if any of you guys are interested in that, do get in touch. We also do cloud-related things still related to the same topic. So if that's interesting for you, then again, do get in touch. I did a PhD in robotics, which was a little bit of a bumpy ride. I started with underwater robots, then with some humanoids, and then ended up with a mobile manipulator. Lots of interesting things. I guess everyone has their own tragic story about their PhDs. And Denis, I think, although Denis has a much smoother story of his PhD, a little longer, but filled with a lot more like very interesting industrial robot applications. And he's playing very humble by telling people that he doesn't actually have the PhD fully yet. But yeah, Denis has been one of the core contributors and also co-maintainers on the ROS2 control project from pretty much the very beginning. Anything else you want to add, Denis? No. All right, let's go. So why do we need a control framework in ROS? So everybody thinks, at the beginning, everyone thinks that their robot is special, that they need to, that they need to develop their own controllers, their own control framework. They're reinventing PIDs and low pass filters. But then eventually you realize that you don't want to write this code. Also, you'll also realize that control is hard to get right. So you get to the part where you end up with this bunch of code that you don't really want to maintain, and you're also not even really happy with it. Because you probably are not good at control theory, like most people are not. Apologies for the exceptions. So ROS control was created as basically a very practical realization of this. There will be a history slide coming up, but basically the main goals are to provide a standardized interface for kind of like high-level nodes to interface with controllers for robot arms, mobile bases, and also some more custom, but still on the standardized fashion, some more custom applications, but still trying to provide semi-standard ROS interfaces. One of the additional goals was to establish a standard set of controllers. One of the, I really like to bring this up as a success story. One of the most basic controllers that we have in ROS control is the diff drive controller. So it solves the control of a differential drive mobile platform that was then extended to handle skid steering and also to handle multiple wheels, still differential drive, and then expanded into like a 4-wheel drive thing, and then an Ackerman thing as well, still kind of like springing from the same code base. And this particular controller was actually worked on by multiple companies at the same time, all using it in their products. So was very happy to see that happen. Yeah, there are a couple more points there that you have probably already read. So one of the other things is is to establish some sort of standardized resource management when it comes to sending commands to specific joints or accessing sensors of the robots, and also to provide a platform to do this in a real-time safe manner. So by real-time safe manner, I mean, if your robot is a little bit more complex than an Arduino, you will probably use a CAN bus or EtherCAT or something more advanced that will require you, that will not really allow you to do ad hoc communication scheduling, but you're going to run at, let's say, a fixed 200 hertz, for instance. So soft real-time safety is pretty important when it gets to robot control, especially, for instance, when you're running a biped robot, a humanoid biped that very actively needs to work to not fall and destroy itself. So that's a little bit of motivation here. And on top of this, we were also, ROS control also ended up providing kind of like a standardized hardware abstraction layer in a way of implementing one's hardware abstraction. So we're going to get into a bit of detail about that later. So let's go to the next slide. I won't spend too much time on this one. So history time. Back in the day when ROS started at Willow Garage, they started with a PR2 robot. And very early, they realized that there's no point in duplicating the code or redeploying the code twice for the ARM controllers, for instance. It's the very same controller. It just needs to be reconfigured. And it also needs to kind of be a little bit coordinated with the other controllers and with the other CAN buses. Oh, no, sorry, actually, CAN buses? I think CAN buses, but please correct me if I'm wrong. So the PR2 had a pretty basic but pretty robust controller manager framework, and then a couple of research robots started adopting the same architecture. Since this framework was very tailored to the PR2, most of these other robots were basically forking it and creating their own versions of the same thing. Some robots were like retrofitted to look like a PR2 to the software. But then like a year or two later, or even already probably at the same time, some of the guys at Willow Garage started working on an abstracted version of that. So removing all PR2 related things and trying to make it a little bit more accessible to other robots and easier to adopt on different platforms. So enters ROS control. I marked it as 2012, but actually development started way earlier, as I mentioned. So 2012, 2013 was the time when it really started to kick off. That was the time when Robotics was also putting like the, let's say the really much needed finishing touches to actually make the framework workable. So the two robots that I put there are, the one on the left is the Ream robot, and the one on the right is the Talos. So for instance, a bit of an example, that the Ream robot is running an update loop at 200 hertz with CAN buses. The Talos is running at, depending, at a kilohertz or 2 kilohertz on EtherCAT. They're both running ROS control. The cool thing about this is that they're running mostly the same controllers as far as their arms and torsos and heads are concerned. And then of course, for walking and for the wheeled base, they have a different controller. And this is roughly the time when the whole project started to get reach a level of maturity when we started to get wider adoption. So ClearPath and a couple of other companies started using the mobile-based drivers. Universal Robot, I think it was Fraunhofer IPA that created drivers for Universal Robot arms. So a lot of things started to come together pretty nicely. And then with the advent of ROS2, we had a little bit of a brainstorming, and we realized that some of the struggles that we were having extending ROS control are basically embedded in the design. So we decided to go with a complete rework of the library, or reboot of the library, and try to incorporate those things from the get-go that we were unable to really add to the ROS1 setup. It's not really related to ROS1 or ROS2, but it's more like it was a good opportunity for us to do this bigger shift. Right now, there you go. So once again, a little bit of general recap of the whole ROS control approach is that imagine that you have an app that will want to use the navigation stack, and it may want to use Move It for some arm motion planning. And then where do you go from here? You buy some robot parts, you put them together, but what do you do now? So the answer of ROS control is that you implement a hardware abstraction layer, and then you just load our stock controllers off the shelf. You configure them with the right joint names and basically everything that relates to your actual robot's geometry, and then you're good to go. What you're gonna get for free with this is a gazebo simulation where you do not need to change a little of there's a little bit of small print here, but typically you do not need to change anything for a gazebo simulation of the same thing, which is a huge gain. I hope you guys all appreciate my daughter crying in the background. Hopefully she's gonna finish soon. So yeah, really cool thing, and a lot of people were. I think that a lot of companies and a lot of research groups had a great advantage of being able to hot swap basically between simulation and real robot. So you could do all your testing and development on simulation and then hop to real robot. Thank you, Denis. Now, a little bit more details about this whole thing. So our robots or our framework is making a distinction between joint interfaces at the level of command interfaces or state interfaces. And then at a lower level, we're going to have different types of these interfaces. So for instance, let's just look at the top side of this figure. Let's say that the base controller is configured to, the base controller is implemented to request velocity interfaces of the joints that it was configured with. And if the robot hardware has set velocity interfaces, these will be provided for the controller when it is requested to start up. And then if everything plays out nicely, the controller is brought up and the data flows the right way and the robot moves, right? We also have, so the other interface or joint interface types that we support in ROS control are position and effort. And the state interface that you can see still on the top figure is a bit of a catch-all. So that's a read-only version. That's a read-only interface that any controller can claim while the command interfaces are exclusive interfaces that only one controller can have access to at any given time. The whole idea with the hardware abstraction layer in ROS control was that, or is that, the robot hardware is only supposed to provide these interfaces to the controllers. What's under the robot hardware is basically your hardware driver. And the robot hardware classes, or like the robot hardware code, is basically what brings these two together. So imagine that you have like a segment of your memory in the computer that has like a flat layout. At least that's what we depicted here for simplicity. A flat layout of these command and state interfaces. And when your hardware is going to look for the command slots to send off on a communication bus, and then your state slots to write data into when it is reading data from sensors. Similar setup. So the second part of the same of this figure is just showing that so the state interface would go and reach for the state values in the vector, and the command one would reach for the state interfaces plus the relevant command interface. So each of those interfaces would provide basically all the states that, like, the states are free to give from the hardware abstraction layer side. So if your controller needs to read positions or velocities or efforts from, like, in terms of state for its calculations, that it can do so, but it is only allowed to write in the command interface. Sorry guys, this is a complicated figure for me. So very briefly, how one would go, but actually we already mentioned quite a lot of these. So once again, it's a bit more of a recap at this point. So the way to implement a robot hardware in ROS control is basically you would inherit from this base class, and then you would implement an initialization function, a read function, and a write function. The role of the read function, obviously, is to read all the data from your robot hardware, from your actual hardware, and the write function is to send all the commands to the hardware. The joint state interfaces, once again, is kind of like encompassing position, velocity, and effort state interfaces, and on top of this, the controllers could gain exclusive access to position, velocity, or effort command interfaces. Implementing, and so this was the first step, and the second step is that you actually need to write your main application, which is the actual node that you're going to start. So, and this setup is basically always the same. If you're familiar with Dave Coleman's ROS control boilerplate, that is one package that basically does this, because Dave was bored of always re-implementing the same thing, and I bet a lot of people were. So I guess there are a lot of unnamed, uncredited ROS control boilerplate packages out there that basically all look the same. So it always begins with building the robot description, which, if you guys are not familiar with it, that's basically an XML format that contains the whole kinematic structure, kinematic and hopefully dynamics structure of your robot. This really helps us. For instance, ROS control can automatically read joint limits and other hints from this description, and definitely the controllers will be interested in distances between links or joint ranges and similar things. Then you go about initializing your robot hardware, which is typically you setting up the communications to your driver, your actual hardware components, and then you initialize the controller manager class, which is basically basically the ROS interface of all of this, the ROS management interface for all of this. And then in the main loop, you just read. That does all the communication from the robot hardware. You update your controllers with this information, which all runs in a single thread, fairly deterministic. All your controllers are always going to be executed in the same order, and then you send all the commands back to your hardware. A little bit limited, but this has been working really, really well for many years. So the standard set of controllers that I mentioned earlier include, but are not limited to, the joint state broadcaster, although in ROS1 we call it a controller. It's not really a controller, it doesn't control anything. The joint state broadcaster's role is to read the joint states to read the state of every single joint in the robot and publish it on the joint states topic. This is what makes your RViz show your robot move. Long story short. Then they already mentioned diff drive controller, which is my favorite controller. Then the joint trajectory controller, which is my second favorite. It has super nice interpolation and preempting of joint trajectories and smooth merging of them. Very, very good, cool stuff. The gripper controllers are, I think, always a little bit underestimated. They are pretty nice, very simple. They're pretty nice, all handling. It's like a kind of like a transformer thing. Transformer controller, right? Give it a try. It's pretty nice. Then we have a couple of we have a family of controllers. Actually, specifically, maybe we could call them 3 families, but there's one big family. We call them forwarding controllers. So in the case where, let's say that your robot hardware already knows how to control your robot because you have a microcontroller where you implemented your super fast control method, or you've got a component that already knows how to control things pretty reliably. In this case, you don't need a joint trajectory controller or a diff drive controller. Let's say your mobile base comes with navigation already. In that case, you only want to convey the basic information to your robot component. So we have these families of forwarding controllers which don't do anything other than simply forwarding the data that they were given. So they don't try to do anything fancy on top. They also come in groups of sets of variants where you can control whole groups of joints as well. So the robots that you can see on the screen are all to some extent using these controllers. So the Valkyrie from NASA on the top left, for instance, is using quite a few forwarding controllers. NASA is very keen on doing their own hardware-based implementations. They also have a whole body control setup implemented with ROS control on top of the robot. The Husky from ClearPath has definitely been using the diff drive controller for a very long time. Similarly, I believe the Grizzly does as well, and the Jackal. I believe the Otto, the first iterations of Otto, the industrial platforms of ClearPath were also using this. Probably not by now. The Tiago on the bottom left is using the diff drive controller for a mobile base, joint trajectory controller for the elevating torso, another joint trajectory controller for the arm, and then another one for the head. The shadow hand is a super nice hand that has also been interfaced with the joint trajectory controller, and they've made some really nice and smooth demos with that really high degree of freedom hand. If you guys are looking for some cool, I think it did Rubik's Cube solving with just the one hand. The HiQ from, I think, ETH, that one actually runs a fully custom whole body control setup, but still implemented with ROS control. And then the Talos on the right does a little bit of everything. It has a whole body control setup, but it also has joint trajectory controllers all around the place. So yeah, that's just a little bit of practical usages. All right, so what was tricky, or what is still tricky in ROS control? And why did we decide to start re-implementing the framework? So one of the things that we encountered fairly early is that as soon as someone wants to go a little bit beyond this trio of position, velocity, and effort, they can't. So these are the 3 joint interfaces that are supported by ROS. kind of in general. So the joint states message, for instance, only has fields for these three. And also considering that effort is a little bit of a wild card. So one could say, oh, one could put acceleration there. Well, not really correct, but you know, it works. Or could put torque or even current sometimes. I've seen that happen. So it's far from ideal, this setup. We also realized that the code base was a little bit too complex, to the point that at some point, like really only a very small group of people would understand how to go about extending the framework in any direction. So too much templating and way too much inheritance, too many layers of inheritance hiding things. And then, as already mentioned, the whole boilerplate phenomena where this control node always had to be implemented for every time someone creates a new, like tries to enable a new robot with ROS control. And then yet again, of course, robot hardware. It's a bit of a catch-all. It's like, this is where you put stuff. We really wanted to make the semantics of the system a little bit clearer than that, especially for the very last point, because we did actually play a little bit with composition of different robot hardwares in ROS control, and it was possible, but it was not a first-class citizen. So you could implement your robot hardware and you could be done, but then that would not allow other people to compose your robot hardware with their own system. There is a kind of an opt-in way where if you implemented your robot hardware as a plugin, as a combined robot hardware, is the name, then that could be now used for composition. But we really wanted to make a much cleaner setup. Now, let's go to the next slide. Are we stuck?
Yeah, I think it's my turn now. Am I right? Or
yeah.
So so what improvements did we do in ROS2 control, or this was main motivation? So basically what we did, we let go this position velocity and effort hard-coded interface types and said, okay, we will use strings describing interface, so we are fully flexible and users can name them as they like. Then we cleaned much of the code base. There is still some cleaning needed on joint trajectory controller, I would say, but more or less everything else is pretty clean now, lean, flat structure, and we use modern C++. Regarding control node, now we provide control node, so there is no need for boilerplates. Basically, everything is in, and one has to also develop less to get the system up and running. Regarding unclear semantics, what we changed was that we added actuator and sensor and system hardware types. I will talk later about them, why those three. And because you don't see robot here, but yeah, robot is actually inside hidden. And hardware composition is natively possible because now it's everything, each hardware interface is a plugin natively and loaded inside ROS2 control, which means that you can stack up your robot cell, for example, with conveyor, some sensor and a robot just via plug and play with few X-acro changes, and that's actually it. So let's look one more time short on the architecture, what has changed here. This first part is basically the same. So we have cool application, we have third-party applications, but then we have ROS2 controller friends, which is like simulation. Currently, we have Gazebo-based plugin for the simulation. And for example, if you want to do mobile manipulator, you will probably create different hardware interfaces for each of those. This means that each of hardware interface can provide different interfaces for exchanging data with controllers. And you are not bind anymore on 3 types, but you can have types what you like, or you can even define your own types of interfaces. For example, if you have your own controller for some special data transfer, you can simply use them. This enables us also to catch the status from the robot very easily. There is one catch or a difference. The hardware interface is not node anymore, which is also on the other side, like from control perspective, better, because you should use always the framework to pipe data out from your hardware to the ROS world. And we added actually one additional component. This is resource management, which takes care about all these components running in parallel, separately from each other. Usually in ROS1, you would actually have them all in one package, so to say. So I mentioned that there is a lot of interfaces, and there is like theory, everything is an interface, which means we can have like infinite number of interfaces. This actually means that we need another message, because join state message, well-known sensor messages, join state message doesn't support this. It supports only position, velocity, and effort. So we created dynamic join state message. The name is not optimal. We had yesterday in the working group discussion again about that. If somebody has better idea, good. But the idea is where we can put all the data. So there you have also for each joint separate interfaces and values for each interface, which can be, this interface can be anything. Of course, we added some standard names. We standardize them like through header definition, where you have position, velocity, acceleration, and effort as standard interfaces. So you don't have to write them as a string, but you can simply use predefined values for checking them and stuff like that. What enables us, enables clarity in interface types. I'm telling always people, please use as clear names as possible. So there is no need to have effort where you put everything, but if you are controlling voltage or current or anything, then write voltage, current, or whatever. Then we have out-of-the-box support for digital and analog outputs. This was a bit of pain if you wanted to really control it through controllers in ROS1 back then. Also, there is a case, and this is not so seldom, that many of current robots have multiple sensors for the same value, which would mean you can have multiple position measurements for your joint, for example, on the motor and on the joint itself, which you need for control. You can have those then simply there. And we don't need templating anymore. We just need a bit of string comparison, and that's it. So the thing what I explained you that we now have plugins everywhere. The question is how to describe this for ROS2 control. Then we need some kind of standardized structure, and we came up with URDF extension. Basically, we introduced their ROS2 control tag, which you would then write for your robot. And this is one example, very simple example. So you define your ROS2 control object, which is in this case robot, it's type system, and loads this plugin. So this plugin will be loaded by resource manager, and you add these hardware parameters for this plugin, which will be directly to the hardware. Actually, all this structure parsed will be accessible from your hardware interface. So you can add here a lot of parameters. There is one nice example on UR robot. I will talk also about them later. On UR robots where there is like 10, 15 parameters here with the different things. You can put anything what you want here. Then you should define each of your joints with their command and state interfaces. So they can be mixed as much as you want. Actually, we don't care, because it's often also that you have different command and state interfaces. Most of the time they're also a bit overlapping, but yeah, it depends on your application. And you can, for each command and state interface, you can define different parameters, or for example, minimal, maximal value, which you want to handle in your hardware. Then if you have, for example, a sensor in your robot, many robots currently have, for example, industrial robots have a force torque sensor on their TCP. You would then define this sensor and define state interfaces for the sensor. And again, you can place here parameters as well as in joints. So you can add additional parameters as you need for your application, also for each joint, for example. And we have one actually wildcard kind of, this is GPIO. We didn't come up with a better name. I came up with the name. It's like general purpose or very generic input outputs. One of the purposes is really digital and analog outputs, what you have on the robots, but also you would use GPIO structure, for example, for robot status, where you have some status bits reading from your robot hardware, and you can then pipe them to the ROS2 control world. And for example, you would like to have a tool, controlling tool, which has one command interface, whatever this is. You would then define it as joint. Joint is basically, it means 1 degree of freedom, something I can command. That's the idea. The thing is, all of this would end up in one plugin. So if you have separate, for example, your robot from your tool, then you would define two ROS2 control like blocks. You can have multiple of those, and then each of those define its own plugin and all the parameters you need there. So it's basically like you stack them together using URDF tag. So on the other side, not only that, since we now can have multiple hardware interfaces, it came up naturally also that you could do some kind of tool changing on similar scenarios, or that maybe you have multiple hardwares, you want to control their life cycle, like you want to stop them, pause them, or whatever. For this, we used also on the controller and hardware side, the reference implementation of managed node lifecycle interface. We are only using interface, so there is no possibility to use ROS services to contact them only through controller manager, but we are using these states for our hardware, basically. This means, so you can check this. We decided to go with a standard version because then it will be known for everybody else what is happening here. Then short, just how to use this. So first thing you would do for your robot, you write ROS2 control tag for your robot or all the hardware you want to use, because this is basically your definition how you do it. Then you implement hardware interface. Of course, this part of it is also parsing of ROS2 control tag, publishing your state interfaces to the outer world, or telling them what they are, and so on. Here you have to decide if you want to use actuator, sensor, or system. Actuator means it's anything which has 1 degree of freedom. For example, each motor, you would then use actuator tag. Idea is here, for example, you want to synchronize your conveyor belt with your robot, and then you would describe your conveyor belt as actuator or its motor as actuator, and you could then control it. Then for different sensors you use in the system, you would use sensor object, or for anything which has multi-degrees of freedom, you would use system. So actually the robots are described as a system. We went with system name because it doesn't have to be a robot in that sense. It can be any multi-degree of freedom. It can be your 3D printer, basically, if you like, anything which is multi-degree of freedom thing. Then, of course, you have to configure controller and controller manager, and this is everything through YAML file. And that's it. The most important thing is there to configure interfaces, so hardware and controller side are matching together. So some examples from the wilderness, let's say, this is here architecture, a bit complicated one, but it's actually, if you want to use robot with Move It, or we have this architecture implemented already in few robots, when you really want to do something with your robot. So the idea is you have your hardware on the left side, and we want to also control it with joystick, for example. Then you need to write the drivers for your hardware. These red parts are custom components. You have to probably write by yourself, but maybe also not if you are using, for example, a UR robot driver or whatever. There is already implementation. There is additional implementation which helps you test the framework of fake system implementation and fake hardware. Basically, the idea is that these fake components, they will parse your URDF and create all the interfaces your real robot has and mirror basically your commands to states, which this helps you. I mean, for me, it saved huge amount of time, because basically you can, without connecting to any hardware or any more complex simulation, you can simply test the complete framework. You can test if your controllers are switching properly, if your interfaces are accessed properly. You can visualize this simple. Basically, it's very simple simulation without any dynamics in it. Then you would use standard, for example, standard controllers, what Bence already mentioned, also to display stuff, or you can program custom ones. And here, in this case of MoveIt, you can do path planning using joint trajectory controller connecting MoveIt, or if you are using MoveIt Servo, which is also cool, check it out if you don't know it. It basically enables you to run your robot using joystick, but also it does collision avoidance and all the inverse kinematics and all the stuff in the background. Another use case or big use case is your driver, which is first actually open source driver with ROS2 control implementation. It also introduced a lot of things what we are working on currently. We added it because of this support, and it's great because it's real world example what everything we should support. So we have like digital analog inputs and outputs. That's basically very important for a UR driver. And what its fun things will come in the future. It's like control generate robot operation, which can be done with UR. It's like protective stop control, a safety restart, brake releases, and similar. And even you can start stop loading programs. So basically, it's the idea you start your ROS2 control framework together with computer starting up, and you can then do everything like with the robot through controller. Idea is you don't have to stop it. Then is also already a dynamic cell implementation with example for Robotics Open Manipulator X. Yeah, probably heard of it. It's also a very cool thing to build up your robot. Regarding other parts, we have a lot of demos in our demo repository where we are showing actually how to use the framework for different use cases. So we have, for example, just now brand new, few weeks old, still hot, tool changing example, basically hardware lifecycle example, which shows you how to switch, turn on and off hardware, and also, for example, how you stack hardware together. There is also a few others very serious robots running ROS2 control currently. Unfortunately, I cannot, I would like to present them, but I cannot, but they are really cool and they influenced, for example, things we are doing here. One of the things is, oh, my robot measurements have offset. How do I control this robot? So we added also open loop control in many of our controllers so that we ignore either state measurements or that we actually separate commanded and measure states completely in the whole framework, but still they are both accessible, which means you can visualize they actually a robot in both positions. You can visualize the measured positions and you can visualize commanded position, which can happen sometimes. And example about this will come very soon. So also there is many other hardware architecture and capabilities what we defined in our roadmap. So check it out, give us a feedback, and yeah, we are happy to check it. So there are also a few references. We will put this presentation also to control.ros.org, our documentation site, so you can then also use it, check it, check all the references. So yeah, this you probably know, ROS control paper and so on. And now, Bence, we are on the end.
Thanks. Yeah. So actually, one thing that that we didn't mention, forgot to put on the slides, is that we also run one of the ROS2 working groups. So, and we have a meeting every second week. So if you guys are interested, then just watch out for check the announcements in on ROS discourse, and just tag along if you're interested to join any of the discussions. So yeah, first of all, thanks guys very much for making it this far. We also have a little bit of special thanks to give to our lovely contributors and the companies behind them, or the companies that were supporting ROS control and ROS2 control from the beginning. So yeah, on the right side you see some important individuals, and yeah, the left side is definitely probably. Let's not talk about the order. So definitely, Robotics has been a major supporter from the very beginning, and I'm actually really sad that their ROSCon talk didn't get accepted. That would have been a very cool one, showing how to implement ROS2 control from scratch on the Tiago robot. Picnic has been really awesome, super forward-coming with all those very practical applications, and that name at the very end is somewhat familiar to me from this other guy that was presenting. Yeah, so yeah, thanks very much. Sorry for taking this long, but I guess the floor is open to questions now.
Yes, it is. So let's try not to do so much moderation. Let's see how it goes. If it's not going well, I will start moderating, but I will allow everyone to unmute themselves. So we can start asking questions, and then if anybody doesn't want to ask the questions, yeah, for the record, the questions are recorded. So just so you know, just feel to type the message in the chat and I will read it out. Okay, whoa, so many questions are coming. So Loy has a question. If my hardware uses, for example, EtherCAT, could I make a generic EtherCAT master that I configure via the URDF extension by adding parameters of which EtherCAT addresses, for example, the position control is at? And Loy hopes he's describing this right. Yeah, go on.
Yeah, Lloyd, this is actually this is the idea of this hardware section, I would say, of URDF. You would do this there. Currently, to be honest, we have idea to start also working on this communication side a bit of libraries, but yeah, resources, time, and whatever. We didn't manage it, but this would be for sure use case.
Cool. Yeah. Thanks.
Or what was your problem in ROS1?
Yeah, I tried to do this. Yeah, it's been a couple of years ago, but I tried to do something like this in ROS1, and I didn't. I couldn't figure out how to do this the way I wanted to. How I could make this generic enough. But in the end, didn't have time to look any further. But okay. I think with what I saw, I think this should be possible now with ROS2. So. But thanks.
Yeah.
So maybe if I find some time, maybe.
I mean, you can put anything here. A good resource for this is really your driver, because Lover actually he's also here. He put a lot of stuff inside. So like everything you need for running robot.
Okay, thanks.
Okay, then was a question from Darko. Micro-ROS and ROS2 control are creating, okay, when should we use micro-ROS to expose and when ROS to control? Yeah, that's a good question. Bence, I will try to answer. You can then answer later. So basically, what I understand micro-ROS is enable you is creating a node on microcontroller, which can then you communicate through ROS2 framework, basically messaging, DDS, and stuff like that. So the thing is there, you can use this as it is, but the problem I see, you don't have any guarantees, for example, when your message will arrive to microcontroller, because at least current implementation of DDS didn't show really real-time safe in these terms. Of course, it depends on your hardware setup. And another thing is, what if you want to do something more complex? So if you want to, for example, synchronize this with robot movement, so if you don't have a pipe, but you have some tool on the robot which you can use, which you can control through micro-ROS, and you want to synchronize this with robot movement and do this in unified fashion, then I would go for ROS2 control, basically. So maybe at some point we set also ROS2 control on microcontroller, but this, yeah, this is a bit probably hard to stick currently.
So the way I may be wrong, but the way I see micro-ROS is I'm not sure if you're familiar with ROS serial, where for ROS serial you would get you would pre-compile with basically the ROS message toolchain and all that stuff. You could recompile the standard ROS messages for any embedded platform, and you could more or less make a native application on your microcontroller that uses ROS. The caveat here is that for ROS serial in this case, and basically anything that would use this approach, also the web clients, is that there's an extra serialization step that then goes through a wire, which is arbitrary. So the way I see micro-ROS is that it's basically that concept, but on steroids, thanks to DDS. So yeah, I would definitely use ROS2 control every time when you need, like, basically your main control framework, and micro-ROS for all your devices, for a ROS native, yet not. Maybe I'm gonna now get scolded by the Open Robotics guys, but a ROS native yet maybe second class ROS citizens. And just okay, so is your question, Marie, related to this? Sorry. Okay, then let me just answer the next question in the chat. So Moon was asking whether the joint state broadcaster is the same as the joint state publisher, and if not, what is the difference? So the joint state broadcaster is the same as the joint state controller from ROS control, which essentially just publishes the joint states message. The joint state publisher is an additional node. I may have lied a tiny little bit when I said that that's what makes your RViz work, but the joint state publisher is what takes the joint states message and the URDF and then creates your TF3 to actually get you the animation and your TF3 in RViz. Although I think maybe the animation works directly with joint states. Probably it does. So it's halfway right.
I think it works at least at some degree direct with joint values. Yeah, but yeah, that's. So you need both. You need basically joint state broadcaster and joint state publisher.
Yeah.
In your setup, for sure. Okay, Marie, would you like to?
Okay, I've got a professor who wants to work with real-time at ROS, and a robot that was designed for Indigo and uses ROS industrial control, not ROS control. I'm wondering, would I need to re-implement the entire hardware interface, or just translate some messages in the proper format?
That is sounds like a very fun project you're looking at. So what I would recommend there is either get the whole platform upgraded by whoever provided it to ROS Analytic, or anything newer. But alternatively, if you have all the source code available, then I think all it would take, if they don't have anything custom and any like large custom code base behind it, then the ROS control API didn't really change dramatically between Indigo and Noetic, which kind of tells you a lot about how far we managed to, what kind of the magnitude of changes that we're able to introduce to the framework itself. So I think you are on the safe side there.
But it's not using ROS control at all.
So we would need to know what that ROS industrial control means. I know that the ROS industrial consortium, those guys have been always very friendly to ROS control. So you may have ROS control there somewhere under a couple of layers.
Mr. van der Hoorn said no. He said something about simple messages, which I really did not understand the connection to either your controller or ROS2, to be honest. Not that good at ROS2 yet.
No. So simple message, this is probably what they are doing. Simple message is meant to be like standard message you send to robot controller. So let me here, I have few cups. So you have your computer, you have your robot controller box, yeah? And depends on your controller box, how good it is, you can define your simple messages parsing in your robot controller box, and then here use just a simple node on your computer and send these simple messages. And they would be parsed. This was the idea from ROS Industrial Consortium to try to standardize communication to your robot with the same messages. So basically that you have only one ROS control node in your computer, basically you would need, which sends these simple messages to your hardware boxes. So idea is to not have multiple hardware interfaces, because current state is you have a new robot, you have to write new hardware interface, basically. If it's not implemented by someone else, you have to do it, because each robot manufacturer has different programs running on the box and stuff like that. So yeah, the thing is actually depends what is actually the robot. But probably the simplest thing would be, if you want to switch, for example, to ROS2, to actually write hardware interface, which creates these simple messages for first, and you send the same simple messages to your hardware. This may not be the most optimal solution, but I think as a first step would be probably the easiest for you, because you don't have to change anything on robot side. If I understand architecture correctly, if you have more information, also ping us on issue list, so we can help you maybe also more.
Thank you very much. That was very helpful.
Yeah, of course.
I really like this next question. Yeah, so it seems like you've went through a very similar trouble than us. So I'm just going to read out the question. So I set up ROS control on various robot platforms before, from mobile bases, robot arms, and even both using combined hardware. Each time it was a struggle because the opacity and many layers, which I think ROS2 control might solve, and the lack of documentation and strong examples. Is there a different approach being taken for ROS2 control? I think the issue with adoption of ROS1 control has been that it's often easier to hack it together yourself rather than parse through the documentation, and roboticists notoriously like reinventing the wheel. Yes, indeed. So actually one of the, I think one of the earlier slides for references, Denis linked to, can we go to the next one, Denis, please? Next.
Which one?
I'm looking for the examples, the example here? Architectures. No, the design document. I think it's the references slide has it.
Here,
one up.
This
there.
one.
Yes. So the approach that we took with ROS2 control was indeed, we know, like I mean, we actually started a whole a new document just collecting good information on ROS control itself, but it was not really enough. We started for ROS2 control, for the whole design process, we started by listing up a couple of these really general FTS is force torque sensor. We started with these with very general sort of abstract applications or setups that we would like the framework to be able to address. And the way we go about development with the framework is that we have a separate repository called ROS2 control demos, which is a little bit more in flux than the others. So expect it to be a little bit less stable. However, that is where we basically try, the approach is that we try implementing one of these that we have in this design document. And then if the framework itself doesn't meet the requirements, then we do an extension for that. So yeah, so ROS2 control demos is probably a good go-to if you're looking for examples. And for documentation, that is exactly why we started control.ros.org, which has a lot, yes, force torque sensor. So which has a lot of extra material that we even pull in from the ROS control and ROS2 control and the ROS2 controllers repository. So we try to go for an approach where we do the documentation in place. So there's restructured text in most of the packages, and these are then all collected and deployed on control.ros.org on a daily basis, actually.
Yeah, so basically here we added different architectures, what we could imagine that this could be used. And the main idea is, of course, here is mostly industrial robot, but it's basically the same. It doesn't matter if you have industrial robot with a tool. I think there is something. Oh, no, we don't have it. But this would be fun. Yeah, there is like industrial robot with external sensor connected to ROS computer. This is basically it. So you would basically have multiple systems in your manipulator. So if you look here, like each of these two guys would be system, like your platform and your manipulator, and gripper will probably be actuator, or at least this one. It depends how many degrees of freedom you have. But basically they are all separated, and you can use only one of them or all together in the framework, of course. Of course, you have to watch out on names of your interfaces. They shouldn't be overlapping and stuff like that, but they are, if you are using Xacro, which I'm always recommending, and I didn't edit here nicely, but we are using in our example prefixes of each joint, then you can simply rename everything very easily and have it very nice there.
Yeah, actually, so one of the reasons why we wanted to go for a separate ROS2 control tag in with ROS2 control, as ROS control would read most of the details from the URDF and then some additional YAML files that you could provide. But for ROS2 control, we wanted to really support modularity more. So along with your URDF, so let's say if you're a robot manufacturer, then you can provide a URDF for your robot component, like let's say the shadow hand at one of the first slides. So those guys, they actually were the contributors of combined robot hardware in ROS control, in ROS1, because it was in their best interest to allow people to modularly to add their own module to any robot. So we actually wanted to a little bit expand on that and allow the manufacturers to provide not only the URDF but also basically the hardware driver, so the robot hardware plugin, so the system component that comes with their component, and its configuration. So you could have like a Xacro file that only needs a little bit of tweaking from your side, but then for the most part, it's just you just need to drop it in your URDF.
Yeah, we have additional question from Darko. Yes, yes and no. I mean, we don't have any concrete plans, but we are open to it. I mean, I would be open because that would be really interesting. Of course, we have to then first analyze what are the limitations of microcontroller, because I think currently we are using C++17, am I right? Or at least C++14. So I don't know how this everything compiles down. Maybe we should snip it around a bit for microcontrollers, but yeah, we are actually open to it. That's why there. Yeah.
Actually, so just one thing I would add to this, like it really depends on whether you mean. I think micro-ROS really targets microcontrollers that run basically hard real time. But I think that so early on, there have been a couple of trials with embedded computers. So basically not micro, basically microcomputers. So any Raspberry Pi variant, and those worked mostly fine. I mean, the problem there, of course, is always that if you're running all this stuff at a high rate, then you're bound to hit some resource constraints. If you can live with that, or if you can avoid it, actually, then.
Yeah, but usually, I mean, I have to say there are good examples, for example, PAL or similar, who are actually running on the PCs or PC hardware, actually in this direction. You can get some very good real time. It's a bit hacky. There is, I think, good description for ROS1 about KUKA driver with preempt kernel, which you achieve a lot already. And if you then also manage to get your control node like stacked to one kernel of your CPU and turn off all the other temperature management and everything else, then you are very far away with your real time.
So one of the things that like at least in ROS1. I know this doesn't make it sound good, but so in ROS1, we definitely have soft real-time guarantees for everything. So that's been very, very heavily tested over the years. For ROS2 control, we don't really have that wide of an adoption yet to be able to claim something like this. But we're definitely writing everything with this in mind. So if you set up your system with an real-time patch, as Denis mentioned, and you kind of, let's say you probably need to augment, or you probably need to write your own ROS2 control node for that. That doesn't use wall time, but instead it uses your custom whatever real-time clock you're using. But then that's a very simple boilerplate in this case. You should be good to go. PID loops. Yes. Long story short, yes. So the position, so all those forwarding controllers, there are some variants where they don't only do forwarding. That was a bit of an oversimplification. So yes, we do have, so ROS control is using what we call the control toolbox, which is not MATLAB, but it's much simpler. It mostly has a PID class, and we're using the same code base for ROS2 control as well. It's a very simple C++ class, just does your good old PID. So yeah, have a look at the forwarding controllers. Again, the caveat is we're not fully aware yet of the adoption, so maybe some of that code may not work as you would expect, but definitely give it a shot and let us know how it works out for you.
We have another question from Rafael. He asked if he should use ROS2 control basically, or he can write his own controllers. I mean, you can write your own controllers. That's, of course, the question is what's there for you. I mean, if you need some forwarding and stuff like that, it will be simple. The thing is where I think it makes sense to look at ROS control or ROS2 control is when you want to extend the system. So you want to add additional sensor. I think it's much easier than, or you will also have cleaner architecture than, for example, if you are using the framework. Because if you are doing on your own, all the resource manager, all the management, all the controller management, you have to do on your own. And here is actually everything done. So that's basically the thing. You have to only take care about your hardware. And if you need some specialized controller, what you are writing, it seems like you probably are using some forwarding controllers, or you are just setting commands from the ROS system. Yeah, you have already everything there. You only need to pack your messages for your hardware in the hardware interface.
Yeah, I mean, and if you don't need any of the ROS tooling, I would just go directly to a microcontroller for hard real time.
Yeah, that's also true. I mean, if you don't use anything, then maybe you don't need ROS at all. Just as a point, but probably you will end up at some point using RVs because, yeah, everybody ends up using RVs or implement their own RVs.
Right, I think we are already past the time, but if you guys still have time and there is one more question, maybe you could answer it.
Yeah, of course.
Yeah, I think
if there is question, we can answer it, no problem.
So last chance, people. No, okay. So thanks everyone. It was really nice. Thanks for very, very interesting presentation. I think I don't know about others, but I will have lots of things to consider now, and I will be looking forward to using ROS2 very soon.
That's nice to hear.
Right. So thanks everybody, and see you in the next meetup then.
Yeah, see you. Thanks for organizing.
Have a good one, guys.
Bye.
Bye.